So today the topic is net zero energy buildings. And at the end, I'll talk about the solar home tour, which is coming up here on Saturday, October the 2nd. So let's define what is net zero. Net zero, zero what? That's the first definition. You could have zero energy, water, emissions, carbon, many things. We're talking today about net zero energy. And there are several different, I don't think anybody's really standardized on which way to put the letters in the acronym, but there's zero energy building, zero net energy, net zero energy, on and on and on. But net zero, and the definition that you'll want to use, whichever acronym you're using, is a building that uses no more energy over the course of a year than it produces from on-site renewable sources. So we'll step through how this happens. There's also another one called zero energy ready, and that is the efficiency first. And I'm going to talk about this a little bit more. It's really the first step to do a zero energy building is to make it very efficient. So if you designing a new building, if you're not ready to put solar panels on the building yet, you should design it where it's much more efficient than code. And that's a zero energy ready building is what you'll hear that term. So then if we're going to have net zero, we have to talk about what's the boundary, what are we bounding, what are we defining the boundary of this issue? And I've boxed the one at the top that's most common is net zero site energy. You can also have source energy. You can think about the, all of the waste going back through the transmission and back at the power plant and try to offset that. That's a pretty big challenge. Another one that people talk about is net zero energy cost. And my house is actually a net zero energy cost home. I'll show you that toward the end as a little case study. There's also net zero energy emissions. You can also think about how are you going to offset the emissions? So maybe you would build a house that's net zero energy in a 2-acre forest, and you'd preserve the forest so that you would offset, some emissions from the embedded carbon in your house. So there's a lot of things you can net zero, but we're going to talk today about net zero energy and net zero site energy. So here's just that little boundary I was talking about. If you have a boundary around your building and your area, you're basically looking at what's crossing the boundary. So you've got electricity, heating energy, cooling energy, fuels. This would be more for a commercial or industrial building than a home in most cases. And then you have exported energy. So if you are using renewables and you're exporting, then you balance out what goes in and what goes out to make it net zero. And everything else is just internal accounting. So as I mentioned, there's really 2 steps. First is create a zero energy building using energy efficiency. That's number 1. So that's the construction, the operation, the maintenance, usage, behavior, so forth. And then whatever energy you need, you produce that with renewable on site. And it could be from solar, wind, hydro, many sources. So let's talk about how they connect to the grid. In most cases, net zero energy buildings are still connected to the grid. There are definitely standalone buildings, but I would say the majority are probably connected to the grid. And you can think of the grid as functioning as a giant battery. You just have some wires connecting out to this grid. When you send energy, it's able to take it and use it instead of like storing in a battery. When you need energy, it sends it back. So instead of a battery providing that, then you're getting the energy from the grid. So you can do it that way. You can also do battery storage grid independent, where you are totally, storing and producing and using everything right in your little box, your little boundary. And then also there's grid tied with a battery so that you can store some, but you can also still interact with the grid. So I have the 3 little diagrams on the bottom of grid tied, independent, and then the hybrid. And they're all valid. It just depends on your situation. So if you are tied to the grid, then the term net metering will be important, because that is setting up your utility meter so it goes both forwards and backwards, and there's some accounting to that energy. Now, unfortunately, net metering, there's no uniform standard in the US or most states, and it really varies greatly by utility provider or location or state. Some might pay you for your exported energy. They might pay retail, they might pay wholesale, they might bank it for you to draw from later, or they may give you nothing for your exported energy. And if you have this, there are still base fees in most cases. Most utilities will have a base fee to cover they still have to have all the transmission and the wiring and maintain all of that on top of the energy they deliver. So there could be a base fee. So hopefully you've caught on that design is very important because you've got to get the energy efficiency up and the load down for most buildings to be able to be a net zero. So I just popped a few of my favorite quotes about design. If you think good design is expensive, you should look at the cost of bad design. Everything is designed, few things are designed well. And that is so, so true. And then thinking about, do you just follow what everybody else wants? Well, Henry Ford's quote, if I'd asked people what they wanted, they would have said faster horses instead of a car. So sometimes you can't get caught in the design trap of doing what everybody else is doing. And you can also think about only those who attempt the absurd will achieve the impossible. And I like to say nothing lasts longer than poor design. So efficiency, renewable generation second. And I've scaled these fonts in about the level of their importance. If you don't do the first one right, you're going to struggle to be a net zero. So how do you do better design? Well, a technique I've used both on a house and million square feet industrial facilities, and it works all up and down the size of buildings, is integrative design. And if you look at how most things are designed, a bad architect, I know there are good architects, but a bad one just draws up a design, something fancy, and everyone else has to make it work. He's got the windows are in the wrong location. There's a lot of west-facing windows, sun coming in hot in the afternoon. You've got to upsize the cooling plant. It's got poor daylighting. There's glare in some areas, no lighting in another. It gets over budget, and value engineering occurs. That's just not the process you want to use, but that is unfortunately the process that we seem to repeatedly use. Whereas integrative design gets everyone together at the very earliest portion of the project and looks at all of the disciplines, and everyone understands what the other needs to be successful and efficient. And the architect becomes really a symphony conductor, and he's integrating all those great ideas into what he's drawing up for the box of the building. Because value engineering is neither. It's a great expression by Amory Lovins, and it's so true. If you go start cutting late in the project, then you didn't design it right in the first place. So how does integrative design work? I like to think of it as loops, and they're loops that just run in succession. So that very early concept and plan is when you should have the most people on board. The construction contractor for constructability, the mechanical engineer to understand how much space you need for ductworks and what the load of the building might be, based on the current sketch. And you go through this design loop and you get a better understanding of what should be done. And then you break out into sub teams again, back to your offices. And maybe somebody said, I'm going to go work on, some details on this and that. And then you get back together and you go through that loop again and you say, all right, what have we improved and what's still left to improve? Then you break out again and you may do some detailed analysis and you come back, and by that third time, you're really ready to issue construction documents for a building that's not going to have a lot of change notices and is going to come in at cost, at your planned cost. So that's the process, and it works beautifully. So let's kind of step through a methodology of design. So the first thing you think about is the passive solar of the project. So the selection of your site, the placement and orientation of the building and the windows and so forth. And then passive features, insulation and infiltration. Once you build that building, if you've made it nice and airtight and you've put the insulation in well, then that's for the life of the building. It doesn't require any maintenance, doesn't require any thought, it just works. Then you start thinking about the solar gain in the windows, exactly where are the windows, what do the overhangs look like. Then next step is the internal load management. So do we have efficient lighting and appliances? Is it controllable? Is it monitored? The heating, ventilation, and air conditioning system is next. So hopefully you've continued to shrink the size of that. So now you can afford to spend a little more on higher efficiency because you have a much smaller unit. If you have water heating, which most places do, can you recover some waste heat somewhere? How can you heat your water efficiently? And then finally, renewable energy. Where are we going to put the energy to run the building? And so if you think about it as an inverted pyramid, good design practices up at the top of that cascade all the way down leads to smaller and less expensive systems when you get toward the bottom. Now, the energy source, if you really want to be net zero, you should pretty much consider doing an all-electric building, no gas, because electricity can produce on site with renewable energy. Gas, you can't really do that. So people will argue, oh, it's more efficient to use gas to heat water, make a water heater. But if you use electricity, you can use heat pump water heaters, you can do waste heat recovery, and then you can produce that electricity with renewable energy on site. The old real estate adage, location, 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 it's very true for a net zero energy building. Where is this building going to be and what are your conditions that you're working with? It's really important to understand all of the elements before you even start thinking about how you're going to place the building. And then knowing where the sun path is and what your shadowing and what your clear areas are. And that allows you to size your overhangs properly so that in the northern hemisphere, you would want glass on the south because the high sun can be shaded with a proper size overhang. In the winter, the lower sun can come in and give you free heating. Good southern exposure, if we're in the northern hemisphere, which most of us probably are. Maybe evergreen trees on the north and the west to block the harsh sunlight on the west and to block the winter winds on the north. Run the axis of the building east and west so you maximize your solar exposure. And here's a little envelope design exercise. If you were going to build a building that were 2,000 square feet, I've drawn 4 different ways that you could do that. You could make a simple square, you could make a rectangle, you can make a 2-story rectangle, or you could just kind of draw a C shape, and plop it on the lot however you want. Now let's compare those. They're all 2,000 square feet of floor area. But if you look at the wall area, how much wall you have to buy, build, and then lose heat or gain heat through, then that varies quite a bit. The square has the smallest amount of wall area. The rectangle is very, very close. The 2-story rectangle, you get quite a bit more wall area, and the C shape has a lot of more wall area as well. But now let's look at south wall, which is the beneficial. So the rectangle improves, it has just a tiny bit more wall, but it has 25% more on the south. So that's good. The 2-story rectangle, you have more wall area now, but you have almost double the wall area on the south. And that's even better. And the C shape has, the south wall area, just the way this one's oriented, happens to be the same as the square. So no gain. Now then you get roof and slab area. The advantage of the 2-story is now you've shrunk your slab and your roof, which tend to be more expensive than walls. And you have to have the land to put it on. You've shrunk the slab. So in general, like a 2-story rectangle, or if you're building a commercial building, you can go up taller, is probably best to optimize all these parameters. And I showed this a little earlier, but passive solar, let's talk about it. The summer, the hot sun blocked by the overhang. What I'm showing on that window is visible light transmission, VLT, daylight. That's good because then you don't need to run artificial lights during the day. The heat can be tuned by selecting your glass properly If you're in a very cold climate, you want to let more heat come in when it strikes the window. If you're in a hot climate, you probably want to reflect more heat out, but that can be tuned. And then the slab, the base of the slab, can act as your thermal mass to hold some of that heat through the colder night. It can absorb sun during the day. So passive solar is a really important technique in good building design. And just the shading, so if you want to do a little math, what's the math on this? You can see here I have an overhang, and I have the length of the overhang, L. I have the height to the bottom of the glass. And if you look at that angle, and you made that equal to your latitude, then that's going to give you a pretty good balance. You're going to get sun in the winter. That low winter sun was going to come in at the equinox, which we just passed here in third week of September, is where it makes the transition. The summer, it's going to be high and not coming in your window. So you get daylight without the heat gain. So the math is, if the latitude is 33 degrees, which is roughly where I'm at, north, and the height of that from the bottom of the glass to the top of the overhang, to the overhang bottom, is 5.5 feet, then that tells me the length of my overhang should be 3 foot 6 inches, so that equinox is where I make the transition. So just some simple math to quickly calculate, and there's some great online tools and programs that you can simulate this with as well. But if you want to just get a rough calculation for a south wall, there it is. So, structure size, shape, and material are important. You don't have to build with what everybody else builds with. There are a lot of alternative systems. We won't go into the detail, but there's structural insulated panels. That's what my house is made of. Insulated concrete forms. You can do earth shelter, straw bales pictured there on the lower left. There's advanced framing techniques which use less wood and allow for more insulation space. And then there's high mass buildings like rammed earth and some other techniques. And I've got a little drawing down there on the bottom right. So infiltration is so important. Air tightness is as important, and maybe more in some cases, than insulation. So attention to detail is needed to get the home sealed up really well. You can do a blower door test where you put this blower in the doorway, and you can measure the pressure differential and calculate how much leakage you have in the house or the structure. So it's a good idea to specify and design for a tight structure and then test it to make sure that you didn't miss something. This is also a very good infiltration inspector, a spider. In your home, spiders will often build their webs in areas where there's a crack and a leak of air, because that's where their food source sometimes crawls and comes in. So spiders, don't squish them. They're sometimes giving you some beneficial information about the leakage in your structure. I mentioned earlier window, almost all windows are double pane, and now triple pane are getting a little more common. What you put in the space is important. Argon is denser than air, so it doesn't conduct as readily. And then I talked earlier about tuning the windows. Well, low E coatings can block infrared radiation and contribute to the comfort level in the home, because radiation is actually one of the big factors in window energy loss. So if you're designing a building, study up and get the right windows for your application. So if we're talking about heating and cooling, maybe first let's start the residential scale. One issue I see is oversizing a system is done quite often, and it increases the initial cost and decreases the comfort, because it'll short cycle, it'll kick on and kick off, and it doesn't really get a chance to dehumidify the air. So you want to shrink the load with good design and then install just the right size system, not too big. And now one technique is to use either a 2-speed or a variable speed unit that can match the load better to what you need to run. So you can run a 2-speed unit in low speed for longer hours to dehumidify better, and it'll still save you energy over running a single speed, on and off, on and off. If you have a 2-story or a large building, zoning is obviously helpful. But you can really shrink the design size of your with good building design. Now, if you're stepping up like to a commercial or a larger building, a couple things to think about are look for heat recovery opportunities for heating and water heating. Consider systems such as ground source heat pumps that use the earth as a giant heat exchanger instead of having to draw heat from the air and reject heat to the air. If you've got a traditional chiller plant, a large system, then focus on system efficiency. If you put in bigger pipes with fewer elbows, you can do smaller pumps, which use less energy. If you use big straight ducts, then you'll end up with smaller fans, which use less energy. And you can also make those all variable speed pumps and fans to match the load. Now, the beauty of a tight building is it doesn't waste a lot of energy. The bad part of a tight building is you don't get much fresh air. If you think about where fresh air comes from in most older homes, it comes from leaks. And that's good, you need fresh air, but with that air comes dust and dirt and energy loss. So when you build tight, you'll need a device called an energy recovery ventilator that can bring in fresh air and exhaust the stale air, but it recovers, over 70% of the energy of that outgoing air. So you're exchanging the air for clean air, but you're swapping the energy content. You're either cooling the incoming air in the summer or heating the incoming air in the winter with your exhaust so that you're not wasting energy. Lighting is really key too. If you do passive solar design really well with the windows in the right place and the overhangs, you end up with great natural light. So if it's a commercial office building where people are mostly there during the day, you won't need much artificial light and the energy to run that. And I think by this point, just about everybody's switched over to LEDs, but if you haven't, don't put any halogen lights or even fluorescent anymore. LEDs are at a great price point and significant long lives and cost savings on operation. So water heating, a few ways you can do that. We have solar water heating, which uses this little picture of our system, basically a little diagram, but some flat panels on the roof that absorb the sun's heat, exchange that through a heat exchanger to heat the water in our tank. And it can be very cost effective. The panels last a long time. I have the panels that I used on my house, I bought used. They were manufactured in 1978, and they're still operating today here in 2021. So I bought them used for $100 a piece. So I think I got pretty good value out of those back in 1996. Another thing is waste heat recovery. If you have a ground source heat pump, a lot of them will have an option to use the compressor to heat water. You can either use the waste heat in the summer or run the compressor. You already paid for that compressor, you own it, it's sitting there in your house. It can provide hot water as well as heating the air. And then there's heat pump water heaters, which are kind of like just a mini heat pump on top of a water heater instead of electric resistance. And it's about close to 3 times more efficient. I'd say at least 2.5 more times efficient than an electric water heater. And again, we don't want gas water heating because you can't produce your own gas necessarily. For a net zero energy home, you'll need to be all electric. Roof is very important. In hot climates, which I'm in, exterior colors should be light for reflectivity. And the roof is the major weak point in a lot of homes. Most roofs are black, not good here for the South. So you want high reflectance, high emissivity. I have a Galvalume metal roof, and it also does a couple other benefits. There's an old expression, you're on the right track when your solution for one problem accidentally solves several others. So if you want to collect rainwater, a Galvalume roof is great because you don't get all the little debris and pebbles off of an asphalt roof that collect up in your tank. It has hail resistance, so it reduces my homeowner's insurance by a pretty significant amount. Has a 50+ year life, so I'm not going to be filling the landfill with shingles every hailstorm. So mine's bare Galvalume. If you have a coated metal roof, it can be even better reflector. And if you're in a commercial or a larger building, a white TPO flat roof is very reflective of the sun's heat. So if you do the design right, you can't just throw your pencil down and say, yay, we're done. There's there's a couple of other things to think about, and you should have been thinking about them in design. But when construction starts, it has to be installed. Whatever your design is, if it's not installed properly and commissioned, then you've wasted your time. So it has to function right. So there's an old expression in the building industry: cost, schedule, quality, pick two. I always pick quality first, cost second, and schedule third. But if you really do integrative design and plan the building, you can do all three. That's the beauty of it. Qualify your contractors and your subcontractors. Make sure your contract language is in there. If you want them to do blower door tests and meet a requirement, there can be financial rewards or penalties that are built into the contract, because money always gets people's attention better than anything. I mentioned certification requirements. Are you doing LEED? Are you going to certify to any kind of standard? And then you need a commissioning team, an independent commissioning team, to make sure that everything is functioning. And then operation and maintenance. If you're in the design, you have to think about the people who are going to be in your building and they're going to operate it. And behavioral issues are usually out of the control of the designer. But if you remember this, complex systems are more likely to be used improperly or fail. And it's hard to find people who can operate and maintain them properly. So I always like to go back to the old Albert Einstein quote: everything should be made as simple as possible, but not simpler. And that really is a great thing to think about when you're doing the integrative design, and think about the people who are going to be there operating the building. Okay, so I covered a lot of design stuff, but it all wraps back to step one, which is efficiency. So hopefully I gave you a few tools for your toolbox that can help you achieve that first step. So whether you're building a zero energy ready home, all that stuff we just talked about is critically important. Or if you're going to go net zero from the start, you had to do all those things before you can get to the icing on the cake. I always think of, solar panels, they go on the roof of the house usually. So they're the icing of the cake. We had to bake a good cake first. So now we're going to add the renewable energy. So the first step, kind of back to one of my earlier slides, we talked about grid tied or a battery system. And most are still grid tied. Power flows back and forth. The downside is solar will shut down when the electric grid is down. There are now ways around that using a battery system and an inverter that's compatible. So it's getting better and better that you can be grid tied and still have some grid independence when you need it. But most systems will shut down when the grid is down. So there are a few that are battery only. And now this hybrid model is becoming more and more cost effective. So how do you size a solar system? I gave a presentation just about a year ago on solar. You could probably go look up that one and get even more detail. But typically, especially if you have an existing home, if you're doing a new building, you should have an energy model so you kind of can anticipate what the usage is going to be each month. But let's say you're in an existing home and you want to add renewable energy. So you would go get your past bills and look at, how many kilowatt hours am I using each month? And then you need to understand your utility provider. What are their policies and how do they handle the excess energy? What's their net metering? So those are two really important first steps. How much energy am I trying to offset and what are the policies that I'm operating under? So most systems are sized to produce, most of the load, maybe match the lowest monthly load. So let me back up a slide. So if you were in an area and you didn't have very favorable net metering, you would probably want to size your solar system based on this example here, where it looks like this house, about 1,000 kilowatt hours, maybe 900 kilowatt hours in November, 950, somewhere around there, is their lowest, energy need. So you'd want to size your system to at least cover that so that you could, trim your bills down without overproducing there in November and October and March and April if you didn't have a very favorable policy for buying back that excess. If you have a good policy, then you could size the system to meet your total annual need and be a net zero home. But again, we're all going to often make decisions that are best economically. So I'm telling you, you might not be a net zero home. You may be a very low use home, but the policies just haven't caught up with your sensibilities yet. Also, sometimes the size is limited by the sunny area of your roof. You may have some trees on one side of the house. You may have a very small roof. But there's a great tool called PV Watts, and I have the link on here, so you can go and look at that. It's a free tool, National Renewable Energy Lab produced. And here is an example output. So up on the right, I put some of my inputs, the latitude and the dollars per kilowatt hour and so forth. And you run this and it tells you, I put a certain size system. Up at the top, it says you will get this many kilowatt hours a year. And here it is by month, how much kilowatt hours and how much that value is at the rate. So PV Watts is a great tool. This example, I used a 5 kilowatt solar system. And you can see, how much energy it produces over the course of a year at a specific location and a specific angle. And you can go vary parameters and see, what effect that has on your power output. But, if you think about this simply, here's that sun path across the sky, right? You've got high sun in the summer and lower sun in the winter. Minimal shade on the panels, facing south at roughly your latitude angle is optimal, but there's some tolerance for 10, 15 degrees either way, and you're really not going to lose a lot. Here in the Dallas-Fort Worth area, every kilowatt of PV panel, they'll have a rating so many kilowatts, will make about 1,400 kilowatt hours per year. And again, go find my solar presentation for a year ago, and I'll go into more detail on that. So if you want to know the cost, so here's that 5 kilowatt system. Depending on the size of each panel, that might be 16 to 20 panels. Say the cost of that for a total installation was $2.70 a watt. There may be some utility incentives. There's the federal tax credit, which is 26% for 2021 and 2022. It may be extended, but if you're thinking about solar, you should at least plan on getting it in before the end of 2022 so you can take advantage of that significant discount. But you add that in even without utility incentives in this case, and it's down to about $2 a watt. Now, if you look at how much energy that produces, say the system's going to last about 25 years, that's producing energy at about 5.7 cents per kilowatt hour. So probably less than you're paying the electricity coming over the wires. There is a database I have linked here that talks about various utility incentives. You can look up your city and see what might be applicable to you. And there is also a link down here to some of the net metering plans in deregulated areas. Again, it's kind of the Wild West still out there, but here are a couple of tools that let you home in and see maybe what you're facing in your location. So I'm just a couple slides. I've talked at the residential level mostly, but a lot of this does scale up. And just to show you a couple of examples in commercial buildings, there's a Walgreens store in Illinois, 14,000 square feet, so pretty good size. I didn't really define EUI, Energy Use Index. It's how many BTUs per square foot per year that a structure uses. So apparently Walgreens' typical store is up in, upper 200s kBTU per square foot per year. So through good design, this store, they knocked it all the way down to 49 kBTU per square foot per year. So they did the first step correctly. And then they put solar and wind power, wind in the parking lot, solar on the roof, and they made it a net zero store. And this is in Illinois. In Arizona, there's a very large 400,000 square foot REI distribution center. They first sliced their load in half with daylighting and energy efficiency measures, and they put a large PV array on the roof. So they would be a net zero building. So if you think, oh, I can't do this on a big building, This is a very hot climate of Arizona. Yes, it's sunny, but it's also that sun makes it very hot. So they were able to do that. In that kind of climate, we certainly should be able to do it in the Dallas-Fort Worth area. So my house is, I mentioned, it's net zero energy cost, and I'll tell you just a little bit more why it's not net zero energy total in just a minute. I'll run through a couple of examples for the house. But we built it 25 years ago this month, actually. We moved in September of 1996 and held our first solar tour about 2 weeks later. We were still unpacking boxes, but we did it. So it's very energy efficient. I didn't add solar PV on the roof there until 2012 when the costs came down. And we've now gone 14 months in a row with net zero energy cost. So hang on. Case study of my house. So here's a little wireframe diagram. The link is there at the bottom. If you want to go see much more detail, I've documented lots of technical information and over the years, a lot of photographs and so forth. But here's all the things we did in our house. Remember, I talked about the 2-story rectangle being the most efficient? That's what we have. Most of my windows on the south. Galvalume metal roof, clerestory windows for light and ventilation, solar water heating. I insulated the perimeter of the slab. We use structural insulated panels. Where I do have windows on the east, I have large deck shading. And I have a you don't see the trees on here, but I have a very wooded lot. So we get lots of shading on the east and west sides when we need it. A few of the features, we kind of went through those in the thing. They're here on the presentation. If you want to glance, and again, you can go to the website and get a lot more detail about each of these. So here is, now remember, we didn't do solar electric when we built. We just did efficiency with solar water heating. So I found some data on a typical North Texas home of a similar size on kilowatt hours per month. That's the blue bars. And then my multi-year average of kilowatt hours per month are the red. So you can see we lopped off, about a third of the energy requirement just from the design. So we did step one really well. It was a net zero energy ready home back in 1996 before anybody had defined that term, I think. Now, when I added solar in 2012, the system was against me. I looked at my past usage. I said, it looks like around 400 kilowatt hours in October and November should be what I size for. So I stepped through, I ended up with about a 3.7 kilowatt system was what I needed for our house. And that would cover about 75% of our annual energy use. So I'm short of a net zero energy home, but the problem was if I overproduced in a month, they didn't pay me or credit me, even a penny. I would be spending money to install solar panels and giving the energy away for free to the utility for 4 months or more out of the year. So that didn't seem like a very smart way to proceed. So I intentionally sized it a little. Let's see. Here were my costs. I had an example earlier. I was about $2.03 a watt back then because I did the installation, so it was much cheaper than going rates were. That netted me. I've been producing energy at about 4.1 cents per kilowatt hour and will for many years to come. And you can see my total cost was almost $7,500. I've saved over $5,000. So if you're looking for a simple payback, it's probably between year 10 and 11. But the beauty is, this thing is going to pay me back big time over decades because I'm offsetting 11 cent a kilowatt hour with producing 4 cent per kilowatt hour energy. Installation, here's another one where the metal roof was perfect. I used these little clamps on the ribs. I didn't have any penetrations. The clamps bite the rib of the roof, and then you mount the rails to those. The microinverters are mounted to the rails, and the solar panels were put on top. So I have no penetrations at all in the roof. Made it very quick and easy, and I could do it myself. All right, I mentioned that I undersized because of the policy. Well, I'm happy to report that almost 2 years ago, Grayson Collin Electric, who is my co-op, made a big change. They are allowing unlimited carryover of excess solar production in any month. And then they also, about 5 months later, they introduced some rate plans. And I started looking at the free nights and weekends plan, and it works beautifully with our daytime solar generation. So I ran all my analysis and my numbers and realized that it would save me money. And so this is kind of complex, but let me step you through. So these are my monthly utility bills starting in August of 2020. That's when my first month on the free nights and weekends plan. So there's a column for my net energy production in the day hours, which are 6 a.m. to 10 p.m. during the weekdays. There's the net kilowatt hours during the day. Oh, I'm sorry. First is total net kilowatt hours. Then I have day and night and weekend. So all weekend long and nighttime from 10 p.m. to 6 a.m. are zero cost for me. I can use as much energy as I want, and the rate is zero. Now the daytime rate, instead of being 11 cents around the clock, is 16.5 cents. So the beauty is I'm producing solar and I'm getting credited for it as it's spinning the meter back at 16.5 cents. So you can see that in the day, I've only had 3 months where I needed to draw from my bank. My bank on the right kept building up. I drew it down a little. Now it's building back up again. It was the winter when we have less sun and it's cold and I'm running, the heater more. But I am a daytime net zero energy user. I still have a little net energy use at night that is zero. So it doesn't, if I put on more solar panels, it really doesn't make financial sense because I'm spending money and I'll just keep building my bank up and I'll never use it. And we have an electric vehicle that we charge as well. So we are running our house and we are running an electric vehicle with zero energy cost, electric cost zero, just the base fee of with taxes and fees, it's $24.40 per month. That's all I pay to live comfortably. So I mentioned the kBTU per square foot per year earlier. A typical house in 1996, when I built mine in Texas, the average use was 41.5 kBTU per square foot per year. Our house, that has come down as codes have improved. I'd say new houses being built in Texas are probably maybe around the 25 kBTU per square foot per year. They've gotten much better than 41.5, but they're still much higher than my 7. And out of that 7 that we need, I'm producing 5.8 with renewable energy. So the pie charts on the right show a typical house energy use, a lot of heating, cooling, water heating, and then everything else. I'm over 80% more efficient than the typical house that was built same size, same climate. And you can see my heating, cooling, very little for water heating, just to run my small pumps on the solar. My other is low as well. We're very conscientious of appliance efficiency and lighting. And I have an aerobic septic system, which actually is a little bit of a penalty. I have to power that, where most people send it down the pipe and the waste treatment plant has to use energy that you're not billed for. I pay for my waste treat energy and I'm still doing better. So back to the multiple benefits, right? Solar energy, here are some benefits. The kilowatt hour price is way less than the utility charges. It'll simple payback in about a decade, but I'll still get at least another decade then of free energy. Low carbon content, no air pollution, uses no water, it's quiet. Solar matches well with the peak load on the grid, so you reduce the load. Local generation means less energy loss. I'm producing and using the power right here. It doesn't have to go through the wires where it has loss over distance. No moving parts, low to no maintenance, and you can get property tax exemption on your home in Texas if you have solar. So it increases the value of your home, and then they reduce that before they calculate your tax, that value. So there's a lot of cascading benefits. All right, so net zero energy, I'm gonna sum it up real quick. Efficiency first, hope you got that by now. Renewable generation second. So there is the annual solar tour. It went virtual last year, and unfortunately it's virtual again this year. Maybe next year people will be able to come out and tour and visit and talk, because it's my favorite part, is getting to meet all the nice people who've come on the tour, and interesting people with great ideas and great questions. But there are two links on here. There are some videos posted, and if you go to my link at the bottom, enerjazz.com/house, I have the link to my active solar video and my passive solar video. You can watch those first, and then on Saturday morning, October 2nd, coming up, they're at 9:30 a.m. The link is on my site. You can link into the Zoom and have a Q&A session. So we will answer your questions about the house and any specifics. There are other homes and other sessions. The link near the top, DFW Solar, will take you. They're actually finalizing the schedule. Hopefully in another day it'll be up, and they'll have the Zoom links for various homes and some of the other links as well. So it's a virtual tour, but the beauty is you can sit at home and eat your Cheetos and drink your favorite beverage and watch the videos, and then pop into the Zoom Q&A. So hope to see some of you on Saturday on that. Georgianne kindly mentioned my book published called The Joy of Efficiency. And it has a lot of details on my house, and including the industrial efficiency design we did at Texas Instruments. So pick that up and read it and steal all the good ideas that you can find. And I'm going to close with a slide that just has some other links. The North Texas Renewable Energy Group is a great group to join. There's a link for Zero Energy Ready Homes. There's the solar tour link again, my house one more time. There's a couple of solar links down there, Solar United Neighbors and Go Solar Texas, if you're really thinking about solar. Some good resources there. So with that, I think we are done with the slideshow.